All right, so let's look at some applications of the exponential functions, okay? Some of these will have a base of e and some of these will not, all right? But we will show how the exponential functions can be used to solve real-world problems, okay? First one we're going to look at is population growth, all right? And this is, a perfect time to cover this with us dealing with the coronavirus right now and being at home from school, all right? So let's look at example 3 here. An infectious disease begins to spread in a small city of population 10,000. After T days, okay, any number of days, the number of persons who have contracted the virus is modeled by the following function, okay? V of T equals 10,000 over the sum of 5 and 1245 e to the negative 0.97 t, okay? Now again, you think about some of the models that have been used to predict the people infected with corona or the people who have been killed by corona, and a lot of the models have been incorrect. Some have been correct, okay? They take the data that they're provided and they build these models using that data, okay? And again, this happens a lot of times, especially with infectious diseases and things of the sort, okay? For these exponential functions, again, we call these exponential growth, okay? So they grow at a rapid pace, and you're going to see that as we evaluate for certain amounts of days in the future from the beginning of this process, okay? And one of the things you've heard a lot recently is flattening the curve. Well, the exponential curve becomes super steep, and one of the things they want to do by keeping us at home and keeping us from being outside a lot of time is to kind of slow down the growth of that curve, the exponential growth there of that, okay? And that obviously would change this function, okay? But for purposes of this one problem, we're going to use this model, all right, and we're going to plug in values and see what happens, okay? So how many people were infected initially, okay? Well, initially means at the beginning of the spread of this disease, okay? Anytime we're talking about the beginning of something, the start time, we're going to say time equals 0. Okay, that's day. That's the first day. Okay, we call it time 0. All right, so we're going to find v of 0. Okay, so again, initially we're going to replace t with 0, both here within the function notation and here within the model. Okay, well, that makes it pretty easy here because e to the 0 power is going to be 1. So we get 10,000 over 5 plus 1245 times 1, which is 10,000 over 1250, which is 8, okay? So when this infectious disease began, there were 8 people who were infected, okay? Now, after 24 hours, 1 day, after 48 hours, 2 days, after 5 days, okay, which is 120 hours, I guess, things would be a little different, okay? And you'll see as we go through this how exponential growth really works. And one of the reasons that we've been home for so many weeks is because they want to flatten the curve and kind of slow down this exponential growth, okay? But again, for this particular problem, let's look at after 1 day, how many more people will have been infected, okay? So again, we're going to plug in 1 for the function. So it's going to look like this, okay? Be careful with the order of operations, obviously. The fraction bar here acts as a grouping symbol, so this 10,000 is alone by itself in the numerator. And down here in the denominator, we have to treat that as one large expression. So we do e to the negative 0.97, okay? Then we'd multiply that by 1245, then we'd add 5, and then we'd do the division, okay? So first thing I need to do is do e to the negative 0.97 power, which would give me this value here, okay? Next thing I want to do is multiply this decimal by 1245, and then I want to add 5 to that, okay? Which gives me this value. Now, when I divide these two to kind of finish it up, I get about 21 people who are infected after the first day, okay? All right, so you can see we've grown from 8 to 21 in just that 1 day, all right? Well, now let's evaluate for 2 days, okay? So I'm going to plug in 2 to my model here and here, okay? So v of 2, v again would be the number of people infected, is 10,000 over this expression here. So again, we want to do e to this power first, negative 0.97 times 2, okay, which is negative 1.94. Okay, so e to that power would be 0.14370, okay? Multiply this by 1245, and then add 5. So it gives us that value, okay? And now we want to divide 10,000 by that, and I get 54.37. So after 2 days, we've grown from 8 to 54 people. So you can see the growth increasing at a quicker rate. Okay, so from 8 to 21, it was just a difference of 13. From 21 up to 54, we're talking about a difference of 33. Okay? All right, so now let's see after 5 days. So we've skipped over day 3 and day 4. All right, so let's see what happens after 5 days. So we're going to plug in 5 to our model. We're going to use order of operations. Okay, so e to the negative 0.97 times 5, okay, is going to be this value here, 0.00783. Multiply that by 1245. Whatever product you get, you add 5 to that. So that gives me 14.74633. Divide these two values. So after 5 days, you would see that about 678 people have the virus. Okay, so again, huge growth. From day 0 to day 2, we only went from 8 to 54. From day 2 to day 5, we went from 54 infected to 678. Okay, so again, great time to be talking about exponential growth. Great time to be talking about exponential functions, because this applies to you basically every day now. Okay, so that's one application for exponential functions.